Hello, this is Sarthak Jain, and this is a demonstration of the final project as part of EE533 under Professor Young Cho. What I'm going to discuss this in this video is how are we going to implement the neural network that will eventually be used in the hardware for classifying networks. So this week, essentially, I worked on the processing element of the neural network, which will then go on to become the neuron. The idea is that whatever data that you get into this module that we have, you'll have a weight, you'll have the actual data, and then you have separate processing elements in parallel that will be running to calculate your calculated weights, which will then be sent out to the other modules for processing. And WP, if I'm to take a subscript P here, this is essentially the parallelization factor. So if we have, say, 3 neurons into the input layer, we'll have P equals to 3 here. So this is the basic idea behind the MBPU, which is the processing unit, the multiplication processing unit that we'll have. And what that will look like is either we can use a separate ALU module or we can use the DSP from the Xilinx library. So this will have a cascaded multiplier and the cascaded adder. This will be the weight and the input data, which is X. Finally, we'll have some sort of activation function here. Let's call it Z. And the activation function's output will be given as a feedback to my summation. Now, this output of addition, this will also be used as in the summation top with the parallelization factor P. So this is the basic idea behind the processing element that we have. Finally, what we are trying to do is to create something like, let's say this is my entire module. What we'll do is we'll have a control module here. We'll have the input RAM, which will have the input weights, the output RAM, which will hold the updated weights after the training. This will be my neurons this MVPU module that I shared here. And then finally your weight cache that will contain all the weights that will be required for my module to work. Finally, the last piece of the puzzle is how are we going to calculate or make that processing element in itself. So the basic idea behind that, we're going to use a processing element. Let me expand the screen a little bit to explain. So this is the processing element module. Let's say this is PE underscore array that we'll have. Now this will house a column multiplier. This column multiplier will have a point multiplier. And this point multiplier will have a reg file along with an arithmetic unit. So the idea is that for the weights to be useful, we do something called matrix multiplication. And this is what the parallelism will help us achieve. So if we have a 3x3 matrix where there's 3 weights, where the weights are embedded in the matrix like this, what we'll do is we'll have this column multiplier where we'll take each column and then we'll take one element from each row, and this point multiplier basically will have column of I times row of I. So this essentially will be used for the matrix multiplication, and this entire diagram will then become part of the PE array. In the code, what we'll see is first we have the column multiplier where we are using the DSP adder here. If we don't want to use the DSP adder, we can use this algorithm where we are using the row I plus 1, and we are basically taking a modulus with the cascaded rows and then using an extra adder here. So essentially each and every sum is going to be pipelined. So if the row I is less than the maximum number of cascaded rows in the second array, in the second matrix, then we'll then pipeline our sum. Otherwise, this point multiplier will basically have us add all the data from the register files. So as I mentioned before, this point multiplier again is using the DSP adder. If we don't want to use the DSP adder, we can use a separate arithmetic instruction, separate arithmetic module that just adds and multiplies the data. Finally, we have the activation function as part of the diagram as I showed. So this activation function will basically have two things. One is the tanh, which ideally takes the input and squashes it down between -1 to 1. And this is incredibly good for classification purposes. And since the project includes classification, we will use either the tanh or the sigmoid function because it's easier on the resources as it's just a basic lookup table. As you see here, whatever data we use, so let me show you how we are calculating the activation function here. Now, if the shift valid is 1, let's say at the end of the reset, our valid shift is taking the data, the calculated data from the DSP and then shifting it one cycle to the right. And this is how we are, this basically decides whether my maximum signal is 1 or 0. And the sigmoid function will basically decide whether it's 0 or between 0 to 1 or it is between -1 and 1. I'm still in the process of perfecting this because I'm not getting the correct data from this, but hopefully when I understand what data to fit into the register file, we'll be able to get this calculation up and running where we are just taking the fixed parameter and just subtracting the integer limit from it to get the table data for the tanh.
So this week we tried getting a bit stream from our design, and we were able to get a bit stream. However, we used too many resources, and we can see from this device utilization summary of our design that we use over 100% of slices, and we use a very large amount of 4 input lookup tables. And in this instance, in this design that we put, our initial design had 10 hidden layer neurons and 10 output layer neurons, but that was too much. We were getting about 500%, 500%. And this design only has one hidden layer neuron. And so this is just to see if we can get a bit file out of a design depending on the amount of neurons that we have. And so in this case, we have over 100% and we have only one neuron in the hidden layer, but we do have 10 neurons in the output layer. So now I'll dive deeper into our synthesis report. And the first thing I'll show is our neuron, our hidden layer neuron. And so our NP dot product is our hidden layer multiply accumulate neuron. And here we have too many flip-flops. And the reason being is because we use a pipeline tree adder. And you can see that we have, for each instantiation of a hidden layer neuron, we incur 1,008 flip-flops. And if we were to instantiate 10 of them like our initial design does, we'd have over 10,000 flip-flops just for our hidden layer. And this is our output layer neuron, which is after our ReLUs, and our output layer neuron incurs 336 flip-flops. And so we have 10 output layer neurons, and this results in about over 3,000 flip-flops. So here we can see that the resource utilization of our neurons are just too much. So now I'll go into our NPU dot product, and here it incurs about 1,000 flip-flops, but also it sees a 512-bit register, 256, 128, and the reason is because we do a pipeline tree addition. And so now I'll show you dot product code itself. And so here we instantiate 32 bfloat16 adders. And then after those summations, we pass those down into another 16 adders, to another 8 adders, to another 4 adders, to another 2 adders, finally to our final adder. And so this is resulting in too large of a resource utilization. And so we need to figure out a way to trim it. And one idea that we have is reusing a bfloat16 add module. And right now, because we have 6 stages, it takes 6 clocks to produce multiply accumulate, because our multiply is just a mux. So once we pass the mux, then we pass that to our pipelined tree adder. And once we get the summation, we pass it on to a ReLU. But the problem right now is, though this is pipelined to 6 stages, each stage, the very first stage, has 32 bfloat16 units, and that's just too much. And so we might go with just using one bfloat16 unit and pipelining it, but that would result in us having a multiply accumulate for a hidden layer 64 cycles for one. And so we're going to try and create some sort of data translation so that we can try and get it to about 10 cycles for each add. And that's going to be instantiating one bfloat16 adder per neuron. But we're still in the works of trying to determine how we're going to decrease the resource utilization with these bfloat16 add instantiations. And now we'll talk about our output layer neuron, and this one we have, right now in the design, we have 10 neurons instantiated for output layer, and this produces 336 D-type flip-flops. And so here is the code for our output layer neuron. And we instantiate 10 multiply units, bfloat16 multiply units. This is our initial multiplication, and then we do another pipeline tree adder, but this time we have 5 bfloat16s, bfloat16 adders, and then we pass that on to another 2, and then we have another 2 here. And so this is our multiply accumulate. In total, an output layer neuron has 10 multiply units, bfloat16 multiplies, and it has 5, 2, 1, 1. And so 5, 7, 8, 9 bfloat16 add units. And this is incurring 336 flip-flops, this module here. And so we need to figure out a way to trim the amount of resources that is being used here. Another problem we have is the timing. So the first problem I mentioned was the resource utilization. Another problem we have is the timing. And the timing is coming from our bfloat16 add unit. And it's producing 16.713 nanoseconds, which results in us getting a clock frequency of only 59.834. And the reason is we pass it through, this is our bfloat16 add unit, and it's all combinational logic. And so now what we're going to do is we're going to pipeline this instead, so that the amount of gates and the critical path length will shorten. And so right now our bfloat16 add, because it's fully combinational, completes in one cycle, but obviously the timing is poor, and so we're going to pipeline it. And so I think what we'll do is we'll create a pipeline for our bfloat16 where we will get the exponent first, and then we'll get the mantissa, and then we'll do some normalization afterwards once we get the mantissa. So we'll account for the denormalized result and overflow and just the regular result as well. And so we're going to be pipelining our bfloat16 add to probably 3 cycles per addition.